Hello physics students. Today we begin our next topic, circuits, or said another way, electricity. But before we jump into the details, I first want to give you an overview of the topic. The first point I want to make is that there are actually two kinds of electricity. You've heard of AC/DC. They're short for alternating current and direct current. In this topic, we're going to confine our studies to direct current, DC. DC, direct current, is primarily driven by chemical reactions like those in a battery. What happens is that at one end, the molecules are looking to get rid of electrons. Remember in chemistry you learned chemical reactions involve exchanging or sharing electrons. So one end they want to get rid of electrons, the other end they want to receive electrons. So you force that tendency through a wire and you get the electricity, the current to flow. So the alternating current, that kind of electricity is what is in your house, in the walls of your house. Every time you plug in an appliance, you are using alternating current, and what's happening there is the electrons, rather than flowing from a chemical reaction, kind of like a river in one direction all the time, what happens instead is the electrons in the wire vibrate or alternate. So they don't actually go anywhere. They just kind of go like this, back and forth, when the circuit is on. And that happens very fast, by the way. The electrons in the wall or in an appliance go like that 60 times in one single second. Okay, so very fast. But again, we don't study that because it's more complicated than we need. We're going to just stick with direct current, which will teach you some basic ideas about circuits and how they work. The next thing, AC/DC, all right? So we're studying DC. The next big point is that there are three main attributes in a circuit. Whether it's AC or DC, there is the voltage or potential, which drives the circuit. Then there's resistance, which sort of opposes the flow of current, which is a measure of the flow of current in a circuit. So voltage, resistance, and current, three ideas. All three ideas are related in what we call Ohm's law, an equation that tells us how current is affected by voltage and resistance. So that's an overview. Today, out of those three ideas, you're going to learn about current and resistance. In the next video, about voltage, which you already kind of know about, and the relationship called Ohm's law. So that's like an overview of the next couple videos. So are you ready? Let's jump in and start with current. Here's the topic, circuits, current. First of all, the symbol used in the Regents curriculum, or actually in physics in general, for current is a capital I, sometimes a lowercase I, by the way. And what it's defined as is the flow of charge per time. It's like a velocity. Remember, velocity was meters per second, distance over time. Well, this is like a coulomb per second. How much charge is flowing in a given amount of time? The coulomb per second is a unit of current. You could say, oh, in that circuit, there's 10 coulombs per second. That's correct, a correct way to express the current. Or you could say there's 10 amps of current. Same thing, a coulomb per second is an amp. Now, this formula, as all the formulas that we study, is on the reference table. And I am, again, in the electricity section, which we began in the last topic, page 4. And as you could see, right here, okay, is our expression I equals delta Q over time. Okay, so there it is on the reference table. All right, now there are a lot of concepts that you need to be familiar with about current and electricity. The first point is that out of protons and electrons in a wire, right? Because they're made of atoms, like copper, for example. It's got a nucleus, protons, and electrons around it. The thing that flows is not the protons. What happens is if I got a segment of wire here, see how I drew it kind of like a cylinder. I put some electrons in here, and all the electrons that are already in the wire shift in this direction, and a different electron than I put in pops out of this end. So it's a little different than water in a garden hose, where when you turn the faucet on, you have to wait for the water that came out of the wall, and you're waiting, and then it starts squirting out the end. That's not the case with the wire, because it's already filled with electrons. So it'd be like a hose that's already full. As soon as a drop of water comes out of the wall, then a drop of water comes out onto your lawn. And so that's kind of a difference with water flow and electrons. The other thing that's could be confusing for you, in the beginning at least, is that when the electrons flow from left to right, we define the current as actually moving from right to left, the opposite way that electrons flow. It's almost like we pretend that the protons are moving in the wire. They're not, but we pretend they are. And you might say, well, if we pretend that, aren't we going to get wrong answers when we're doing our calculations for current? And it turns out that that is actually not the case. You can pretend protons are flowing in a wire for almost all your calculations, and then only later, if you're asked about it, you say, oh no, the electrons are going the opposite way. So current's going this way, oh yes, electrons are flowing that way. How can it be that that doesn't make a difference on a macroscopic scale? Well, think about this. Let's suppose current, instead of current, let's say we want wealth to flow in this direction. You got me standing here, you standing over here. One way I could transfer wealth to you that way is I could take positives, dollar bills, and start handing them to you that way, right? And then we got dollars, positives going that way. I'm getting poorer, I'm losing money. You're getting richer, you're gaining money. But another way, let's suppose we weren't allowed to trade dollars. What you could do instead is you could take credit card bills out of your pocket and start handing them to me. So the minuses, the bills are going this way now towards me. What's happening? You're becoming less in debt. You're giving away your debt. Said another way, if you're becoming less negative, it's almost like you're becoming more positive. Well, it is. Same thing. You're getting richer by getting rid of your credit card debts and giving it to me. I'm taking them on. I'm getting more negative. I'm getting poorer. Or in other words, I get less positive. So in the end, it makes no difference whether electrons are flowing this way or positives are flowing that way on a macroscopic scale. While there are a few situations in physics where it does make a difference and you really have to do your analysis as electrons flowing in this direction, but not in this course. Again, you just pretend positive is flowing that way out of a battery and you're perfectly fine. So let me give you a moment to copy these notes down. Okay, so another point that I want to make about current flowing in a circuit, it's not so simple like this where all the electrons sort of migrate nice and smoothly this way. Electrons are trying to fight their way through the wire, which is made of atoms. And electrons are like blind. They don't see, oh, I got to walk around and move around these atoms. They're sort of pulled in this direction. And as they're going along, they bump into atoms and other electrons along the way. So the motion is kind of chaotic. You see how sometimes I see this is where the electron started, this is where it ends. Sometimes it's kind of going in a forward direction and it hits an atom right here and it ricochets backward like this. And then it starts going this way, this way, this way. And here again, it's going backwards again. So I just kind of made like a random zigzagging, forward, backwards, left, right. But overall, it's drifting to the right. So there's random motion on top of what we call a drift velocity. And that's the net result of the electron flow. Okay? Why is that important? Because the electrons don't have a free movement through the wire. They have to kind of struggle in a sense. So there's almost like a friction on a macroscopic scale. When you throw something and slide across the floor, there's a friction that slows it down. There's a similar kind of thing that happens to the electrons as they're flowing. The motion is opposed by what we call resistance. Okay, so we use, which takes us to our second of the three ideas, right? Voltage, current, and resistance. Today we talked about current. Now we're going to talk about resistance. The symbol we use for that is capital R when we try and quantify exactly how much resistance there is in a conductor. The unit of it is, we say, an ohm. That's how you spell it out. It's from the Greek alphabet, the omega symbol. And it looks kind of like a horseshoe, okay? And that's so how, this is how you draw the unit, okay? So every conductor has got a length to it and a certain sort of width to it, a thickness. Now, most conductors, when we have wires like in your house, they're made cylindrical, which is what I drew here. There's a certain length to the wire, the cylinder, and there's a certain cross-sectional area. When you cut the wire and you look at it, it's a circle, usually pi r squared, but it doesn't have to be. You could have rectangular wires if you wanted to, and they would work just fine. Well, the resistance, you can calculate it if you need to with this formula right here. This is a Greek letter, rho, like when we learned Greek, the mu symbol for friction, right? Well, another one is rho. It looks kind of like a P, but you start down low and you go up like this and around like that and make kind of like a funny curly P. This is L, length over area. This formula, by the way, is also on the reference table in the electricity section. Actually, you know what? I have to go to this camera later for my example problem, but it's right here, a little bit below the current formula. So I'll show it to you later when I go over to the camera a little later, okay? So there it is. And what this formula says, it captures the concept, some concepts. First of all, this symbol right here, resistivity, let's hold off on a second. But what it says is that longer wires have more resistance. Kind of makes sense. If you want electrons to go from point A to point B and they have to go through like a mile of wire, well, that's going to be more resistance than a little short wire, right? So more length, more resistance. That's what we have right here in this graph. And thicker wires have less resistance, okay? So that kind of makes sense. Like if you want to have a lot of electricity flow, you got to have a thick wire, which is what we see in this graph here. So let me create a pause to allow you to copy this down. Okay, so the relationship's expressed here. Now what I'm going to do is an example. Oh, I also didn't mention what this resistivity is. Well, let me ask you this. Imagine you have a wire made of copper and another one made of gold, or another one made of aluminum or steel. All these things would conduct electricity. But if you had the same exact shape, area, and length, would you really think that a copper wire would have the same resistance as a steel wire or a silver wire or gold wire? No, the different atoms, the different elements would have different resistance for the same length and area. That's where this symbol comes in. And again, I'll show you where to find that for the different kinds of metals when I come and bring the reference table closer to the camera. So let's hold off and let's move on to the example. Example 1. Determine the resistance of a 2-meter long copper wire with a cross-sectional area of 2 × 10⁶ meters squared. This is about the cross-sectional area of a wire that, let's see, I guess maybe if I put my hand like this. This is a wire that powers a typical bedroom in a house. You see that end of the wire right here, right? If you cut it and you look at that closely, it is actually a circle, okay? So that the area of that circle is tiny, right? It's a really small area. So that 2 × 10⁻⁶ meters, I measured this radius and I calculated it would be about the area of this wire, cross-sectional area that might feed your bedroom for your lights and your alarm clock and your computer. This is the thickness wire typically used in a house. This is another household wire just to show you. This is what's called a service wire. And so you could see, well, let's see if I go like this. The approximate area compared to my hand, you see it has 4 wires inside this one larger wire. The the area of one of those is a lot bigger than what we saw. In fact, it's a bundle of smaller wires. This is about enough wire to feed a house. 100 amps of current could pass through this wire because of the resistance being so small. So it gives you an idea of actual physical sizes of wires. But again, we're using this thin wire for your bedroom. We're trying to figure out what the resistance of 2 meters of that wire is. So there is our example. All right, here's our formula we begin with. Now we need to plug in the pieces. Well, the length and the area, I had them. But where did this resistivity come? So now I'll come with a reference table and show you the few things that I wanted to, I held off on. The first is that formula for the resistance of a wire. R equals resistivity length over area. Okay, that is in our electricity section right here, right? So you see it's in this set of formulas. The resistivities, they are, let's see, right here, okay? On the bottom right of this, you see that we basically have a bunch of, a table with a bunch of metals, and right where my thumb is, you could see copper's resistivity of 1.72 times 10 to the minus 8th. That's the number. You can't forget the units up here, ohm meters. Okay, a lot of students forget that. They put the number and they forget the ohm meters. From these numbers, you could see copper's a pretty good conductor because the smaller this is, the less resistance the wire will have. So copper's pretty good. But look what's better. Silver's better. It's 1.59 instead of 1.72. So we would have better electrical flow in our house if we use silver wires. Why don't we use silver then? Obviously, it's more expensive, too expensive. Copper's good enough, okay? But you see some metals, and you could look up more. Another thing we're going to talk about also tomorrow is this 20 degrees Celsius. These values change when the wire changes temperature. But at 20 degrees, 1.72 times 10 minus 8, that's what I'm going to plug into my formula right here for resistivity of copper. Punch that on a calculator, and you get 0.0172 ohms. Small amount of ohms. That's why we use copper wire in our houses. Okay, so let me create a pause to give you an opportunity to copy this down. All right, let's do another example with this equation right here. Okay, so one more example for today. All right, so this is going to be a little bit different than the example we did before. We were talking about with wires. In a solution, you could actually have positives flowing because all these ions, like let's suppose you dissolve salt in here. There's sodium and chlorine, and they're just sort of floating around the water. You could have chlorine move one way and sodium the other, and that's perfectly fine. So what you would have is, let me give you some data. So let's suppose we've got moving this way, we've got plus, let me make up a number, 10 coulombs in 2 seconds. Maybe those are like the sodiums migrating away from this positive wire and being attracted to this negative wire. And then going the other way, we have negative 10 coulombs in 2 seconds. Okay? So on the surface, it might look like the current's zero because we've got charges flowing this way, charges flowing that way. But remember, the I of the positive charges is definitely moving to the right, so current of this data is actually this way. I of the positive charges. Positive is flowing from left to right. But the negatives, if minuses are flowing this way, this side, this wire is getting poorer because it's getting minuses. This one's getting richer because it's getting rid of minuses. So this is actually getting richer, more positive. So the net current caused by the flow of the negative ions is also this way. Remember, current of minuses is the opposite way of the flow of the ions. So what I have to do is I have to calculate the current of each of these, and rather than subtracting them, I actually have to add them. So let me fill in those pieces. All right, so if you need a moment to catch up, I'll create a pause to allow you to copy this down. All right, so let's move on and calculate the two currents. It's going to be 10 coulombs over 2 seconds, which equals 5 amps. And for the negative, it's also 10 coulombs over 2 seconds, which also equals 5 amps. Again, don't put in the minus here. We already included the minus by switching the current around to be consistent with the previous part of the problem. Now, the net current will be equal to the 5 amps from the positives plus, not minus, the 5 amps caused by the negative. In other words, the net current is 10 amps and it's going to the right. So let me create a pause to allow you to copy this down. All right, one final point I want to make about the calculation of current. Be careful when the time is given in minutes. Pretty common on the Regents to try and trip you up. If they tell you a certain amount of charge passed in 1 minute, you have to actually plug in 60 seconds here. 2 minutes, 60 and 60, or 120. 3, 180 seconds. 3 minutes, 180 seconds. Always time has to be in seconds. All right, so again, today we learned about current, I equals delta Q over T. And we learned about resistance. R equals resistivity, L over area. Current is kind of like the flow of how fast charge is moving. And resistance is kind of like a restriction that holds back the current going through a wire. So tomorrow I'll mention voltage again, and then Ohm's law, which puts all these three ideas together. So I hope you enjoyed the physics. I hope you enjoyed the video. I'll see you in the next physics video.